Welcome to this video in which we will be covering Jacobi and Gauss-Seidel method. These are iterative method and we will see what is an iterative method. We will see what is the solution of a linear equation. Then we will discuss about the diagonally dominated system, Jacobi method, and at the end Gauss-Seidel method. So iterative methods are those in which we have some initial solution vector and then we try to find a sequence of approximation which is denoted by xk. So generally solution is represented by x, that is solution of a linear equation is represented by x. If we have a 3 cross 3 system given here, it may be written in vector matrices form like this, where denote x is used to denote the solution of the system. For convenience, we may write this x in this form as well. So this helps us to write it in a very convenient way. So what is diagonally dominated? A diagonally dominated system is the one in which the absolute value of the diagonal entry should not be less than the sum of the absolute values of the off diagonal entries in a row. So we will see in an example what do we mean by it. So Jacobi method and Gauss-Seidel method, they must converge if our system is diagonally dominated. Consider this system. In this system, we can see that uh, we can see that 3, 4, -1. These are the entries in a row in which entries in a first row where the diagonal entry is A11 and off diagonal entries are A12 and A13. We can see that the sum of A12 and A13, I am talking about the absolute values. The sum of the absolute values of A12 and A13 is 4 and 1 is 5. So sum is 5, whereas the diagonal entry in this case is 3. So we know that 3 is less than 5. So diagonal entry is less than the sum of this. So in this case, we can see that it is not a diagonally dominated system. So whereas if we rearrange the same system in some other way, and we make 5x plus 3y plus 2z equal to 17 as the first row, then we can see all the entries, they are the diagonally dominated. We can write the coefficient matrix as 5, 3, 2, 3, 4, -1, -1, 1, 3. And in each case, we can see that diagonal entry, which is 5 in first case, is equal to the sum of the remaining entries. Diagonal entry in row 2 is 4, which is equal to the sum of the remaining 2 entries. I'm talking about the absolute sum, absolute value sum. In row 3, the absolute value should be 3, and sum of the remaining entries is 1 plus 1, and in this case it also satisfies the diagonally dominated condition for all rows. So we may say that the system is now in diagonally dominated form. So in general, we have an n cross n system, and we can write this n cross n system in the following way: that x1 may be obtained from first row, x2 may be obtained from the second row, and similarly, xn may be obtained from the x row. And here x1, x2 up to xn represents the component of the solution vector x. So what I mean if I consider a 3 cross 3 system, then x1, x2, x3 may be represented as this, and this expression is obtained from here. I just uh, I just take these two values to the other side and then divide everything by 5 in x1. And similarly, I can obtain the rest of the values too. So what is important to note? Important to note here is that you will not find any x1 term on the right hand side when you find the expression for x1, and in x2 you will not find x2 on the right hand side, and similarly in case of xn you will not find xn term on the right hand side. So this is the type of the system which we write. And now, what is the Jacobi method? Jacobi method is the one in which we find new iteration xk with the help of previous iteration, which is denoted by xk minus 1. So here I can represent everything in mathematical form. We have xk minus 1, mean k minus 1 iteration, and we can use all the component in this iteration to find the new iteration, which is named as xk, and this method is very simple. In component form, in compact form, I can write the Jacobi in this way, and here x ik represents the kth approximation of ith unknown or ith component of x. So what is a Gauss-Seidel method? Gauss-Seidel is a bit technical method in which we use each updated component as soon as it is updated to find the new iteration. So we find each updated component as soon as it is computed. So let's see what we mean by it. Let's say this is k minus 1 iteration in which each component is represented by this. We'll update x1 by using the first equation of the system, and then we'll write this x minus 1 as x minus x1, our newly found value of newly found values of the first component, and remaining component are not updated until. So we will continue this process, and what we will do, we will update x2, then x3, and so on xn to find the new approximation. So this is how we do. We use x1 in all component. We will use the previous value to find x1. When x1 is found, we will use that value of x1 here, the new value of x1 here, and remaining values are old. And similarly, we will continue till we reach at xn, and we'll see that there are many new values and over here. So this is the compact form of it, that for ith component, we will use I minus 1 new values, and then from I plus 1 up till n, we will use old values for the Jacobi method. So this is the comparison of these two. In Jacobi method, we use the previous value. In Gauss-Seidel method, we use the updated component. So in Jacobi method, new iteration xk is obtained with the help of previous iteration, but in Gauss-Seidel method, we use each updated component to calculate the new iteration. So now we'll see an example of it. Let's consider this system, which is in diagonally dominated form. And from here, I can write x1, x2, and x3. So this is the expression for the Jacobi method, in which we are using the previous values. Let's say we have initial guess as 1.5, 1.5, and 1.5 for all three components, and then I can compute first iteration by using 1.5 at each for each variable, and the new solution, new iteration is 1.9, 1.25, 2.667. Whereas in case of Gauss-Seidel method, I have to use some new and some old value for, and purposefully I have written x, y, z instead of x1, x2, x3, so that I may recognize that which one is Gauss-Seidel and which one is Jacobi. For Gauss-Seidel, I have used x, y, and z, and for Jacobi, I have used x, y, x1, y, x2, and x3. So you can see over here that we are using some new values and some previous values. So let's see how we can proceed. So similarly, we assume that initial case is 1.5, 1.5, 1.5. We will use this value, and you can see that how we use this value. For y naught, I have used 1.5, and for z naught, which is not updated so far, I have used 1.5 to compute my x1. So I have some value of x1 now. Whenever x is over here, I will use this new value, and for the rest of the variable which we have not computed so far, I will use the previous value. So in this way, I can compute y1, and then both are used in the last iteration. So I will use here these values to get z1. So by doing so, I can write the iteration which is 1.9, 0.95, and 2.35. So this is the method which will be used. So first I will explain, or I will solve the problem with the help of Jacobi method, and then I will solve the same problem with the help of Gauss-Seidel method. So as you know that in Jacobi method we use the previous value. So in all the cases I have used 1.5, 1.5, 1.5, 1.5, 1.5, 1.5 everywhere to get this new iteration. So in case of second iteration, I will use these values. This will be for x, this will be, I will use x2 as 1.25 and x3 as 2.6667. So I will use 1.9 over here, 1.9 over here, and so I will use 1.25 over here and 1.25 over here, and similarly I can use rest of the values to calculate the new values which are the second iteration, and then I can use the second iteration to calculate my third iteration. So in this way I can calculate the third iteration, and I can go on till my answer repeats in the next iteration. So you can see that after 170 iteration, it will be repeating, and I will get my answer. On the other hand, when I solve the problem with the help of Jacobi method, Here you can see that I am using x, y, z for the variable or the component of the solution. So I can write this equation from the system, and initially when I try to find the first iteration, I use the value given, and I can calculate the value of x1, which is 1.9, I think. So if I calculate this value now, whenever there will be x, I will be using this new value. So this is uh, the procedure that we will use in Gauss-Seidel method. So you can see that it was 1.9. So in this case, I computed this value for x, and when I want to compute y1, I have used x1 the new value and z1 the old value. So with 1.9 and 1.5, I can calculate the y1. Now, when I try to calculate z1, both of the values that will be used over here, means x and y, both are available, and I will use both of these values to get z first iteration. So in this way, I can calculate the first iteration. Now for the second iteration, I have this initial vector, and to use this vector, I'm going to calculate the second iteration. So in the second iteration, so for y1 and z1 will be old values from here, and using these values, I can calculate x2. The second iteration. Now, when I have x, I will use this value, and I will get the other variables. So 1.89 over here, and the previous value of z here, and 1.17 is the answer, and both these new value will be used to calculate the thing further. So this is the method that we generally use for the calculation of variable in Jacobi method. So we can calculate the third iteration as well, and we can continue the process, and we can get the answer in 91 iteration. So we calculated the answer in case of Jacobi. We required 170 iterations, and here we have calculated the answer in 91 iterations. So this is the difference between both of the cases. So if you have any question, you may ask.